Hello and welcome back to Calculus 2. It's been days. So now we are going to talk about disk method. We're going to talk about volumes, very specific kind of volumes. Mainly Calculus 3 is the course that deals with volumes and how to compute volumes of irregular shapes. Today we are going to exploit certain geometry to figure out some formulas on how to find the volume of particular objects. So all of the objects that we will be considering in 6.3 and 6.4, with skipping certain stuff, will have one of the cross sections to be a circle. So all of those objects are obtained by rotation. So this marker that I have in my hand is almost a cylinder, and it's obtained very simply by rotating a line around x-axis, and as you rotate, you get the shape. Another object, if you disregard the nozzle on top, so you just look at this, right? Once you can put it on the x-axis. X-axis is going to go straight through the middle of the object. So if you have this particular function and you rotate that function around x-axis, you will get this bottle. We can find exactly the volume of this bottle by figuring out what is the function that we have over here. So straight line, and then, I don't know, either x squared or e to the x or whatever curve fits this description here. And then you perform the integral that we're going to learn today, the formula, and you will get that object. Anything that has the circular base will be, you will be able to compute. So that bottle, lift it up, this bottle has complicated function, right? Because if you look at the side, it's not just a straight line. Thank you. Not just a straight line. Now, you have your bottle, that's the Starbucks thingy. That bottle does not fit our stuff today, right? Because that is kind of squarish, right? It's not circular, it's not round. It's mostly a square. Does anyone have a cup? Oh, there's the cup right there, the red one. Can you please lift that? So this might end up being a project for you guys where you will actually take a cup like that and figure out its volume and then match it by what company claims that the volume inside is. It could be one of the problems for the project, which is hands-on. Then you have all of the other kind of cups and bottles and so on that you guys might have. So what we are requiring today is to have, when you cut the object, it has to have a circle as the cross section. So even if you look at the clock at the wall, that clock, if you cut it in a particular way, will have a circle as the cross section. So what we are talking about is having, let's say, a linear line like this, and if you rotate that on x-axis, what you get is a tube. You will get a tube, which is obviously a cylinder. So you started with f of x, so let's say y equals 1. A line between values a and b on x-axis. A lot of shapes fall into this category, so this is technically the marker I was talking about. Any kind of pipe would be this. But then, you can take a look at shapes and try to figure out what would they get you. If you take, let's say you take a line segment like this. So what would line segment like this give you? Nope.
Kind of like a cone without the tip?
Yes. So what is it?
Wait, it's not a cone. My project.
What happened?
You say a cone without a...
Yeah, the cone without the thing.
No, thing.
So what is it? Truncate cone. It's going to be a cup. All right? It's a cup. All right, let's see if you can do better next time. How about now? Baseball bat. Good. Very good. Light bulb. Anything that ends up being round when you cut it in a particular way. So baseball bat and cups and bottles and technically anything that has a tube, it's going to be like this. Now you can get the cone if you want the ice cream cone. Not a season, but that's okay. You can have right there. You will have a cone. You have to get used to this type of visuals now, because if you're engineering, this stuff will be machined, and then you have to kind of, especially if you're going to go into engineering graphics and other courses. So this is something that you should be able to turn in your head and create the object. What do you get if you turn half of a circle? What do you get? Ball. Right? So if you have this, you will get the ball. I got lazy, so I'm not drawing the objects on the other end, but you can ask our artists to chip in. Right? Half a circle?
Yeah, I thought you said bowl, like a cereal bowl.
Oh, bowl, like
That's what I thought you said.
bowl,
That's what I thought.
and then bowl.
Mm-hmm.
Yeah, it's just English is just terrible. All right. So we would like to know what is the volume of these objects. If they are hollow inside, how much liquid would they hold? If they are solid inside, how much material do we need to actually make those objects? And then we'll see, we can upgrade and have combinations of these things. Like you have, let's say, imagine an ice cream cone, which is actually a solid piece. So there is no room inside to store anything. It's just a solid piece. And then you drill a tube hole, right? Just a hole through the middle. So you actually have a cylinder that looks like this, but it has the hole right through the middle. So what is the volume of something like that? We'll be able to compute all of these things. So now we are going to examine one of the cases. I'm going to start with, let's say, a cone that stretches from A to B, and I'm going to have my delta dx, right, delta x, the one that representative rectangle which swipes from left to the right, swiping all of the values x from A to B. I will write the formula, and then we will discuss and figure out what the formula means. So volume for the disk method, and this is the formula that we are using, so we will be boxing this. Make sure it's big in your notes. Volume is pi integral a to b f of x squared dx. And I'm going to box this. I will also add for this formula that rotation is on x-axis, because right now we are rotating on x-axis. Now we're going to upgrade this formula and make it better, but this is the introductory one. Just
Is f of x squared or is x squared?
f of x squared, the entire function. Now we'll see what that, right. So first of all, dimensionally, does this make sense? We know that volumes are 3D concepts. You have two dimensions coming up from y squared, and you have a third dimension coming in from dx, because technically what this says is y times x. That's what this fx squared times dx is telling you. This dx is the distance between a and b. So it is three-dimensional, clearly, because I have these three multiply each other. So cool, we are getting the volume. And now to solve the problem, let's say this is 2 and this is, I don't know, 7. We can find the volume easily because we can figure out, it's a linear line, we can figure out the formula for it, which is y equals, it's a negative slope, 2 units up, 7 to the right, x plus y-intercept is 2. So it's very easy for us to figure out this particular formula. You don't really, want to go crazy about, the bottle over there for Poland Spring, right? You got to model it now again, because those functions are not as easy. Oh man, there was such enthusiasm. So what is the volume? The volume is going to be pi times 0 to 7 on x-axis, because dx is going to swipe between 0 and 7. The function that we are dealing with is negative 2 over 7x plus 2. And then we have everything squared, and then we have dx. So now all you need to do is to FOIL solve, and you get some numbers at the end. Pi. I didn't time that right. I wanted to say pi through sneeze. Didn't work out. I panicked. So pi, we have to square everything. So we have 4 over 49 x squared minus 8 over 7 x plus 4 dx. And then the integral is still 0 to 7. And now we integrate each one of these. So x cubed over 3, so 4x cubed over 3, so 120, 147, I hope. Minus 8 over 14, that's over 2, cancels 4 over 7. X squared plus 4x from 0 to 7. So now what I do is plug in the 7. Now quick computing, if you guys are interested, pay attention. It's going to be 4 times 7 times 7 times 7, and the bottom was 49 times 3. So 2 7s are going to die to 49. So technically you have, right, only that. Minus 4, again I have a 7 squared, so 4 times 7 times 7 over 7, one of these dies, plus 28. And for 0, everything just dies because, right, they're all polynomial. You have to be careful with the 0 plugging in, because cosine of 0 is 1 and e to the 0 is 1. But for polynomials, it just kills the whole line. So in our case over here, we have 28 over 3. There's a pi in front. So 28 over 3 minus 28 plus 28. So these two cancel out, and we have 28 pi over 3, which is roughly 28, right? Pi is 3.14, so they roughly cancel if you want to estimate things. But 28 pi over 3 should be a good answer, I hope. Yes, no? Anyone? No matter? All right. Or you can just use your calculator. So that was an example. Well, units cubed, whatever units cubed, because it's volume. If they, feet, meters, centimeters, millimeters, inches cubed, anything, depending on what kind of unit you started with. Units of the graph. So is this 2 inches or 2 feet, right? That will be inches cubed or feet cubed or meters cubed. So now we're going to take a look at another example. And this example is we want to rotate the parabola, let's say. So y equals 3x squared plus x minus, no, just 3x squared is fine, it's just too much. 3x squared plus 1, nah, just so it's a little bit annoying. Rotate around x on interval 2 to 4. All right, so do it. Yes, right. Yeah, it should take an hour. Yeah, every Calc2 problem takes an hour. So we draw our picture, which is going through 1, and then say from, let's say, 2 to 4. We are rotating this shape around x-axis. We draw representative rectangle. That representative rectangle is dx, and that helps us set everything up. So volume is pi integral 2 to 4, and we have 3x squared plus 1 everything squared dx. We get pi integral 2 to 4 of 9x to the 4th plus 6x squared plus 1 everything dx, which further gives us pi 9x to the 5 over 5 plus 2x cubed plus x, everything computed from 2 to 4, and that's equal to a number, and the problem is solved. All right? Good. What happened?
Computed like the old one.
What do you mean old formula? This is...
I thought it was just like a regular function. I didn't square it.
Oh, you didn't square it. Yeah, that syndrome was around, and hopefully we get rid of the syndrome. So you have to memorize the formula. As you can see, we're only doing Calc 1 integrals. The entire chapter 6, guys, is you memorizing formulas. You are memorizing formula for disk, for washer, for shell method. You are memorizing formula for length of the curve, and then surface area of revolution. Entire chapter 6 is you memorizing formulas and figuring out how to set something up. Calculation-wise, everything is either basic integrals from Calc 1 or U sub. And then chapter 7 switches on you when you learn new integration techniques, which might be applied to formulas from chapter 6. So you are not learning any new techniques. You know what you know from Calc 1. The entire thing in chapter 6 is memorizing these formulas, getting used to the fact that now you have f of x squared. You have to plug that in correctly and use it. Well, there will be some concepts as well, but we're not learning new techniques in terms of integration. Next problem for you to practice before we switch it up a little bit. Oh, just give me a second. So the next problem, let's say, what are you going to hate? This one probably. 24, we are rotating around x-axis. The formula is y equals secant x, which is trapped between y equals 0, x equals 0, and x equals pi over 4. Yeah. Oh, by the way, welcome to Calc2. Did I mention trig? There it is. So all you need to do is to graph it, and then take a look how, yes?
If we do without graphing in exam, it won't matter.
Next example will show that it matters, but I would say it doesn't matter in this particular case. But yeah, just let's see what you get. Integral of secant is not a basic integral. It's ln of secant plus tangent, but you don't need it. Integral of secant is ln of absolute value of secant plus tangent. And we'll learn that later in chapter 7. You don't know this. Graph of integral of secant. Yeah, I just told you this morning.
No kidding. I don't know.
Then turn it the other way.
Your skin, not the actual your muscle.
I forgot too. They don't have it.
Bunch of smileys and frowns, okay? So the smiley, frown, smiley, frown, smiley, frown. That's the secant graph.
There's no interval though.
And every time you have a vertical asymptote in between. Yeah. So those of you who did not take pre-calculus 2 with me, which is all of you, the way you graph these functions, secant, cosecant, and cotangent, is you draw parenting function, you cut along the x-axis, and you flip it out. So if you want to graph secant, just get my ink stopped. Now let's go home. Yeah, I ran out of ink. I was just kidding. He's not messing around. This guy's already packed. Are you kidding me? I have new batteries in the bag. It's just all over there. So. All right. So how do we graph secant? The graph secant, you graph cosine every time when cosine hits the x-axis, because secant is 1 over cosine. When it hits the x-axis, that's where the 0 is. It becomes a vertical asymptote because you go over 0, right? And then you flip all of these out. So there's your smiley, frown, smiley, frown, smiley, frown. The red one is the secant. Now we have 0 to pi over 4. 0 to pi over 4, it hits right here. That's pi over 4. This is where pi is. Pi over 2 is the asymptote. So 0 to pi over 4, if I extend this way, this is the shape that gets to be rotated. Now, sure, you can wing it and few examples without graphing, but you'll see very soon that without graphing, you just can just look at it and cry and then walk away. Have to know how to graph. So in this case, it was easy because nothing special was happening. We have volume is pi integral 0 to pi over 4. And we have secant squared to integrate, which is an easy integral. What's the integral of secant squared? Very good. What's the tangent of pi over 4? All right, whatever. Yes? Y equals 0 is the x-axis, so it bounds the object. You have 0 from the left, pi over 4 from the right, the function on the top, so you are actually boxing in the area.
We will say tan pi over 4 is 0.
Tangent of pi over 4 is 1. Tangent of 0 is 0. So, it's pi.
We will say it's 0. Yeah, but yeah, I think.
Please don't.
Maybe it takes it out the tangent of pi.
I don't know why I have two equal signs, but I have two equal signs, so here's a single equal sign. All right. Next problem, you're going to love this one. I promise you. Y equals 0. Y equals ln x. Oh, yeah. Y equals ln x. Y equals 2. X equals 0. Rotation around y. So common sense is that you should do what? Yes? Yes, write the equation in terms of y. Excellent. So volume is pi integral c to d of f of y squared dy. That's the y version of the problem. All right, let's see what you get. What happened? Are we all good on this one? No, exactly. We're not. We gotta figure it out. Life is tricky. Gotta get up and do things all day long. What happened? So we start with the graph. to figure out what is the region that we are rotating. Now we all hopefully know that ln graph looks like this. It goes through 1. And then we're going to have 2 somewhere on y-axis. So this is the region which we are rotating around y-axis. What do you get? Funnel? Nice. So what you get is something that looks like this, right? Whatever it is, it's going to be solid, so it's flat on top, flat on the bottom, full of material inside. But that's what you get. It has a very sharp edge. Look at that spike right there. That's an edge. So this is extremely sharp around, and it's because of here, right? This is where the base would be, like that. So that's how the shape looks like. Right? So now my representative rectangle is right here, dy, and that representative rectangle is going to move on the x-axis, it's going to move from bottom up. So as I am setting this up, we're going to have volume equals, I have never been more comfortable in my life. I just realized that. The way I kind of position, I just, this class will now be officially like 5 days long. All right? I know that Domino's delivers on campus, so yeah, we're not leaving for days. Volume is going to be pi integral from 0 to 2, because the rectangle will start on the bottom, on the x-axis where y is equal to 0, and it will rise up, swiping all of the values between 0 to 2. And now I have f of y, but all I have is y equals ln x.
You do the ln of b, that becomes 1 over b to y.
Okay. So e to 2y, right, because we have to square it, and then dy. This is how awesome Calc2 is. So we have pi, the integral of e squared is e2y divided by 2, computed from 0 to 2, and you guys cannot ignore 0 now, because e to the 0 is 1. So we have pi over 2, you can kick that out as a constant, and you will have e to the 4 minus e. No, minus 1. That's exact value. You are free to go and calculate your whatever 100 it is. Right, e to the 4, you have roughly, yeah. Good? Okay. All right, so now what we are going to do is we are going to extend this to 2 functions. So what happens if I have a parabola piece intersected with a linear piece rotating around x-axis? Well, the progression that you had from Calc1 to Calc2 in terms of the area under the curve and area between 2 curves was you subtracted, right? Well, you do the same thing now from A to B. If you compute everything, would be the top one and then minus the bottom one. So this method is called washer, and this is the actual general case. It is the one that you want to remember. Volume is equal to pi, swipe again A to B, and then you have the top function, f squared, minus the bottom function, g squared dx. Now obviously f of x and g of x, right? And you also have the volume pi c to d of f of y squared minus g of y squared dy. So these are your formulas. Not too comfortable with the mouse, but I got it. Okay, so now that you know this one, solve problem 28. Y is x, and y is the fourth root of x. How do we find limits of integration? Yes? Set them equal to each other. Good. So you know everything. You have to graph because you have to know which one is on top. The only way how you know which one is on top, which one is on the bottom, is if you graph it. So we know that, oh, rotation is on x. I forgot to say that. Apparently, everyone in the classroom is stuck, so can't solve a problem without knowing that. So you have a 45-degree line, and then you have x to the fourth going like this. I mean, fourth root. So we are rotating on x-axis. This is the shape we rotate. And clearly the fourth root of x is on top. So what we do is we set equations equal to each other to solve this and find all of the roots, right? Wherever they intersect. I mean, hopefully you see it's 0 and 1, right, just because of the equation. But then you can go to the fourth both sides, get x to the fourth equals to x, subtract x over, factor out x, and then x is 0 and x is 1. So they intersect at 1 and 0. So my representative rectangle is going to go, which is dx, is going to go between 0 and 1. So as I am setting the problem up, you hopefully see that it's essential to know this representative rectangle, because representative rectangle is going to start all the way to the left at 0 and swipe through the entire shaded region, which is 1 to the top, right, to the right. And then you have the top and the bottom of the rectangle, top always touching f, which is fourth root of x squared, minus bottom always touching the bottom function, which is x squared, and all of that dx. Perform a little bit of this algebra, right? So square root of x minus x squared. You should be able to compute from here, right? I took Calc 1. Pi x to the 3 halves divided by 3 halves minus x cubed over 3. All of that computed 0 to 1. Now polynomial, so we don't have to worry about 0. 1 preserves all the values. Pi 2/3 minus 1/3, which is pi over 3. Units cubed, right? It's volume. So going back to the definition, the formulas that you are memorizing, these are called washer method formulas. And you have to realize that this is the general case, because every previous case we did, this was 0. Right? If g of x is 0, if there is no other function, then it's 0, in which case is the previous formula. So you're not memorizing 4 formulas in this section. You are memorizing one formula, which is this one. And then you realize that if it's only one function, then we don't need this piece. You realize that if it's a y rotation, then it's this one. So you just change c to d and make everything in terms of y. And when you're doing this sideways rotation, it's the one that is further away from the axis of rotation minus the one that is closer by. The same thing happens here. We say top minus bottom. But top is the further away from axis of rotation than the bottom. So it's top minus bottom. If you put this sideways, it is one that is further away minus the one that's closer by, again, to the axis of rotation, in this case, vertical y. So you are learning, I mean, some of you will say, and then you have to memorize all 4 formulas. But if you use a little bit of common sense, you see that the only thing you need is actually this one here. Because this one is identical except with all y's. That's if you rotate around y. And actually, I should write that. I should write that this is a rotation on x, and this is a rotation of y. I should write that. So we are clear. Because the next section is going to interchange them. For rotation of y, we're going to have dx. That's the next section. Hopefully you figured out when you did your class prep. So in 6.3, we skipped that first part with the slicing because that's done in Calc2 like this. So don't waste time. And then the bulk of this lecture is in this rotation. Maybe we can do one more rotation problem. You want to do one more, 6.3? I don't know. You tell me. All right. Yeah, something tells us you're going to regret this one, right? Nah. It's going to be epic. So rotation is on x again. And we have y equals square root of sine x. Y equals 1, x equals 0. So these three alone should make the box. Remember that at any point I'm just going to go around and ask you, tell me the name of the person sitting next to you. Yeah, well, you can't solve the problem without the graph.
5, and then final 1 is pi half.
I'm just, like, what's our A and B?
Yeah.
Oh wait, hang on, are you telling me square root sine x and y equals 1, or those? Oh,
Yeah, go through like this.
What did you get for? No, it's not that. Your computer has to be memory mode. One, great. That's just
Ooh. Window, -1 to 1. Okay, that's more obvious.
Yeah. It kind of touch, but like not really.
One, oh, never mind. I think you can find that out. I think there's an intersection of what it is.
How's it going, guys? Is the square root of x fun?
No.
Why not?
Wait, what's your like? I don't know, what are they? What's your Mexican name? No. Yeah, your tribal name. You can try that. Wallace? Is it really Wallace? That's what it really is. The top one, right? With the bottom cover.
Yeah, they do.
What's happening in the bottom? Oh, it's just the other side.
Yeah, yeah, it's imaginary part.
Laughing so like cat.
Yeah. Yeah, you did not graph square root of sine x. You graphed sine of root x.
Oh.
So whatever we graph the sine, and then we use the gradient.
Yes. So now we see the graph. So what we are going to do is we see that the intersection of this happens at what? Top is 1, yeah, but what's here on the bottom? Yeah, I'm asking what's the intersection point. Nope. Pi over 2. Yes. So it's pi over 2. And now, this is why you need the graph. When you rotate around the x-axis, you can rotate one of the two things. This is where the cutoff is, right? No, I missed that one, but that's where the cutoff is. Do you see how you have two different areas? You have this area here and you have this area here. So which one do we want? We want the purple one, yes, the pink one, whatever the color is. What was the color the other day? The magenta? Magenta. Yes? Well, that's what we're going to do now. It has to have a representative rectangle which is touching both functions. And you see that there is a function y equals 1 that has to be touched by the rectangle. If you draw a representative rectangle on the bottom, this rectangle will never get to touch function y equals 1. So this is how we know, and it's important because we need to know which one is on top. In this case, 1. So when I set up the volume, pi integral 0 to pi over 2, we're going to have 1 squared minus square root of sine x squared dx, which is further equal to pi integral 0 to pi over 2, and we have 1 minus sine x dx, and then we go from there. What's the integral? Integral of 1 is x. Integral of negative sine is positive cosine. We compute from 0 to pi over 2. So that's pi, and then we have pi over 2. What's cosine of pi over 2? 0. And then we have minus 0 when you plug in 0 into x. And what's the cosine of 0? Yes. So that's the answer. It's pi and then pi over 2 minus 1. Now you could go and get the decimal answer that no one cares about, or you can just leave it there as the exact answer. What's up?
I did everything without the graph. I mean, it works.
The winter is coming, all right? Some of you know what that means. The others, it's just cold. It's much more. So much more than that. We're going to stop the stream because we are done with 6.3. After you're done with your soup, we'll start with 6.4.
Actually, it's chilly.
After you're done with chili. Yeah, that's the